Hey everyone, how are we doing? I say William is here asking about number 5. Is this on the new assignment? Let's go ahead and take a look at that right here. What do we got? Got some for loop. Seeing all the good stuff right here. Let me hop in. Let's take a look. I'm pulling up the assignment as we speak. I think my brain is rebooting. How are you doing, William? Assignment 3, you bet. Let's go take a look at some assignment number 3. Getting it loaded up right here as we speak. Assignment 3 loaded up. Clear out some stuff in R right here. And let's go take I'm finding the buttons. Let's go take a look at this. I'm doing well. Just getting my second cup of coffee. Just waking up. Sit up straight right here. Stretch out. And do everything good. Got a good workout in. This not between class this morning and just waking up. Let's take a look at this. Question number 5. Here we go. We're actually probably going to need the homework packet for this. Make sure to remember the homework packet is located over on the modules. Let's go over here to the modules. You know, maybe I can make the homework packet a button. You don't want too many buttons. So we go over here to homework packet. And here's the homework packet. And there's the opening of the homework packet. And let's find the question. Question number 5. Let's throw out some Mubot points too. Mubot, you awake? You around here?
I am Mubot.
He's around all the time. People are getting tons of points. Love it. And number 5 is going to be... Did I leave this part? No, that's the random samples part. Number 5 says... Question 5. Good, here we go. Question 5 says... number 6, A and B of page 72. A and B of page 72. Let's go to page 72. Looks to be... Is it... I think it's this one right here, right? Exercise 6. Here it is right here. So this is exercise 6, parts A and B. Can I copy paste it? Make my life easier? Let's go over here. And here it is right. How do I keep on... Oh, good. It's just going to take a random sample. Yep. So let's put a random sample right here of our student ID. That's not a real student ID. So replace the numbers right there. It's just a random number. And there we go with set student ID. We're going to load up reg class. We're going to take the random sample. Everything works. Good deal. And then we might have to use the suppress warnings function, which removes additional warnings if you get like there's a chi-squared issue that can happen sometimes with the approximations. We're curious to see if there's an association between the size of party and whether or not someone smokes. The parties range in size 1 to 6, which is a quantitative integer amount. It is appropriate to compare the averages between the groups when y only takes on a few different values. Using the average is typically the best way to do so regarding distributions. Run the associate, perform a test of significance using the default value of permutations. Why is the test inconclusive? Now, you could get, and we'll see what I get, it's possible you might get conclusive results. If so, maybe comment on that. I'm the one grading it, so not too big of a worry. I'll look to see if your results are conclusive. One thing you want to make sure you do, so you might manipulate the seed. Trying to think of how much this I want to answer. Let's look at this. You ready? We're doing smoker or size of party. And we're doing size of the party and whether they smoke. So we'd be seeing whether or not, let's look at the variable over here. Here is we're using the EX tips data frame. And here it is right here. And you can see the data over here. Always take a look at your data to see what's going on. You have different variables. We have whether or not someone's a smoker and the size of the party. You can see the size of the party vector. Just so you can see a good look at this, here's the smoker, and the size of the party is going to be over here on the far right. So all of this good stuff for us right there. So let's go here to size of party. You notice it's not auto-completing because it's inside a data frame. So make sure you type it correctly. And smoker data equals survey 10. No, what am I doing? EX2 tips. And you need to do this. You need to do seed, spell seed correctly, equals. You could probably put 320. We'll see what we get. Figure's too large for margins. That means you need to change the box right here. and it will, of course, scrunch your screen a little bit, but you can then get it to print out. Do we get conclusive or inconclusive results? The answer is, luckily, our results are barely inconclusive, which is something we went over today. Awesome, William, you're seeing it. So why are our results, and I think you're seeing it right here, so that should, why are our results right here inconclusive? Why are the results when comparing the mean inconclusive for trying to figure out, and this is something we went over today, which is really good. Why are the results right here inconclusive for comparing the mean? So we're trying to see if there's differences among the mean amount of people in a party for smokers versus the mean amount of people in a party of non-smokers. And then the question is, why are our results inconclusive? Well, the p-value is not statistically significant, but the results for determining if the results are conclusive or not on statistical significance, we reach the result of inconclusive, and the answer is right over there. The reason being is because this contains 0.05. If you do not get inconclusive results, I would highly suggest changing the seed. The seed will control the randomness. When you knit, it'll do the same thing. These results are even more inconclusive because it contains 0.05 to a greater degree. So once again, if you do not get conclusive results, I would change the seed. These results here are inconclusive. So I'm getting a lot of inconclusive results. Inconclusive. Maybe we'll finally get a conclusive one. I could make it conclusive by doing, this is actually conclusive significant. So change the seed around. This one gave me conclusive significant results right here. And you'll notice that right here that 0.015, 0.047, you see conclusive significant results right there. The interval is significant because it's completely below 0.05, and it's conclusive because it does not contain 0.05. And we went over that. So many people. Here it is. Oh, that's all right. That's all right. Ask any question you have. Here's where you can see if an interval is statistically significant or not, and if it's conclusive. The p-value right here will tell you if something is statistically significant. This is statistically significant, and this interval is conclusive because the interval is completely below 0.05. If your interval contains 0.05, which we see in some of our output, the previous output contained 0.05 on it. So when you get an output that contains 0.05 for a p-value, then that interval is inconclusive on whether or not it's statistically significant. This interval right here is conclusive but not statistically significant. Down here, this interval is conclusive and is statistically significant. It is statistically significant because the interval is completely below 0.05. It is, well, the p-value itself is statistically significant because below 0.05, and the interval is conclusive because it does not contain 0.05. So when we talk about intervals, we're really talking about, is the result here conclusive or inconclusive on whether or not it is statistically significant. When we're talking about p-values, it's a simple below 0.05, yes, statistically significant, above, not. This one here, although higher than 0.05, is conclusive because every value is higher than 0.05. Very important thing to see right here when we're talking about the notes. Here is a not statistically significant interval where the values would all be above 0.05. Here's an interval that has some values below 0.05 and some values above 0.05, and thus we're left questioning whether it is statistically significant or not. A little bit back, black and white thinking, but great explanation. Oh, thank you, yeah. And so what we do right here with the estimates, and great to have you here again, what we're doing right here with the intervals is we're seeing, we're estimating the p-value through simulations. So we're asking, it could be that the p-value is below 0.05. It could be that it's above, and we can actually increase the permutations to make a tighter interval, and this is what we're talking about today. More questions if you have them. William, are you working on part B? Let me know whatever you're working on right here. It's open time right now to take questions. What did part B say? Ask those questions. Let us know. Part B says change it to 5,000. And what is 5,000 going to do? It's going to, it's basically increasing the sample size. So when we increase the sample size, we're going to see a tighter interval. Now, it doesn't mean the interval is going to go down and go to a lower p-value or go up and go to higher p-values. It's just going to make a better estimate, because that's what we're doing with simulations right here, is we're estimating the p-value via random chance permutations, where we just randomize the results. And we were looking at that at the end of class today. We were asked for an example. There's the reduce the size of the interval. Exactly, Trace. Great answer right there. If you didn't see it at the very end of class, we were asked for one more example of permutations, to where here's a data set on whether or not people were studying for the test. So if you see right here, people's grades on the test, made up data set. Person 1 studied yes and got a 99. Person 2 studied yes, 93. And these are just someone's grade. And if they studied, this person did not study and made a 66. Now, what is a random permutation? You could randomize both of them, but as long as you randomize one of them, you're good. If you notice what I did here, I'm creating the same data frame, but I'm sampling the grade to randomize whatever grade someone gets. So now it's like when I take your test and I just throw them in the air and I say, take the one that's nearest to you. Well, it doesn't matter if you studied then, because whatever grade you get is just random to the test that falls nearest to you. So this is a data frame created by a permutation, a random orientation of the data. So let's take a look at what happens in a random permutation. Now the person, and it could have been they got a great grade, but no. You see, 2 people got great grades, but this person studied and got the lowest grade. This person did not study and got a pretty great grade. We could see what else could happen. Harry, good to see you. Or is it Hari? Good to see you. Ask any questions you got. Let us know. We're just looking here at the random permutations and what would happen by random chance. And that's what we're doing with these permutations to say what is likely, Harry, there we go right there. What is likely to occur by random chance? And this is a small data set, but we could see it with much larger data sets. Like we could say what would happen with larger data sets. And to maybe mention tomorrow's topic a little bit, which is associations part 2, let's go here and do something. I want you to think about the relationship that height has to weight. Just when you think about someone's height and their weight, like if someone is taller, generally speaking, you would expect them to what? Like I have a friend who's 5 feet tall. I have a friend who's 7 feet tall. You would definitely expect the people who are taller to weigh more. And you can see it right here. That as, and we could flip it, I said taller weighs more. So here we go with X being height. Generally when people are taller, they weigh more. We see a little bit of weird non-linearity down here and some outliers. A huge outlier down here of somebody who's 75 inches tall and weighs 75 pounds. Not that I've looked at this data set before. Don't worry about this extra command right here. This is how you make a linear model. And I guess I'll do the good thing of accessing the data frame it's appearing in, but you'll see the classic stuff we've talked about with y tilde x comma data equals. And now I'm going to append onto this AB line M. What's even better is we have a function in the reg class package, which will just visualize the model for us. So it actually creates the visualization of the model. And so we don't actually need to do the whole plotting thing because we could go through here and try to replicate this, but it's all done with the visualized model M, which visualizes the linear model. You do see the outlier once again, the person who is 75 inches tall and 75 pounds. You do see some bit of non-linearity, especially here at the bottom. You see some heteroscedasticity, all these major issues, which we will talk about as we start to talk about regression. But I want to ask you this. If we were to randomize this, what do you think would happen by random chance? And let's change this here to where we're going to sample, and I think this should work, and create a model now that would be just by random chance. And what do you get? Oof, it really doesn't like that. That's so interesting. I like what it's doing with the graphic. Let's not use the... It really doesn't like that. I've never done that before within this, and love it. Oh, it's so crazy. You know what I could do? Is I could fix it by doing the following. I could go to survey 10. I could go to height, which is the one I'm randomizing. And then inside of height, I could sample survey 10 height. So now I'm overwriting it with a sample. And then I'm going to take the same line of code I have written here, but I'm going to remove the sampling. It doesn't like that function. I didn't know it would do that. It's my first time writing it that way, but here we go. Much better. Any jaggedness you see right now is just the jaggedness you would get from it trying to do certain pixels. But that's how it should look. Now, if you look at this, these are all random chance permutations, and I've destroyed my data set as we're speaking right here. But notice how the line is mostly what right here? The line is mostly what? Who can explain that most of the time? Sometimes we see something bigger. I'm trying to find a big one again. But the line is mostly what? Actually, that was one of the best ones we got by random chance. The line is mostly what by random chance when you look at maybe the correlation or linear association between two variables where they're by random chance, because we're just randomizing the data when we run this code right here. Line 32 randomizes the data. Line 33 creates the linear model. Line 34 visualizes the linear model. Most of these relationships we are seeing right here are very what? Flat. Great job right there. Yeah, these are all just by random chance. Now, if I reload my data set, I should be able to repair the data. And we can compare what we're getting right here to the ones we just saw by random chance. And here's our model. So think about our model versus what we see by random chance. our model looks very what by random chance when you compare our model right here to the models by random chance. And these are all random chance models as we scroll through them. And when we finally get to our model looks to have a relationship that is very what by random chance. This is where the p-value comes into play. Our model looks to have a relationship, and there's the p-value down here. And that's literally what a p-value means. The p-value is telling us that our model, I hate that it wrapped the screen right there. And there it is. It's in scientific notation. That is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That should be it right there. There it is. There's the p-value telling us that it's very unlikely by random chance. And actually, you're right. By random chance, the sign will actually flip around. If you notice, it's positive, negative, positive, negative, negative, positive, positive, negative, positive, negative. All these random chance have a very flat, or the coefficient of the slope would be very close to 0. And we don't see that in our model. In our model, we see a coefficient of the slope that is far away from 0. And what's interesting is we actually have another function here to talk about the possible regressions. And this is such a cool little thing. It's just for teaching purposes. This shows us the reduction in the sums of squared error we're seeing with our model. And here's the models we would get by random chance. And if you notice, this is graphing for you all the lines you're getting that were kind of those the flippy floppy little lines that just kind of stayed around 0. So by random chance, you're likely to see a correlation close to 0, which would be a flat line if we put the regression through it. But our line, graphed here by the red line, and there's outliers, there's problems with this model, there's heteroscedasticity, there's non-linearity. This is not the best linear model in the world. But there's strong evidence that the reduction in sums of squared error, which is what we do in regression, we do a reduction in the sums of squared error, which is the variation within, because we were talking about this yesterday, especially within ANOVA, the variation is being drastically reduced in a way that is extremely unlikely by random chance. So here's a really great question. The most likely reductions in sums of squared error when we do a model, if it's by random chance, the most likely reductions, or what we would expect the model to explain, would be closer to what? And you can see the answer here in the graphic. Reductions by random chance are probably going to be closer to what? Like if we have random chance reductions, or when you think about it like an ANOVA, the top part of the ANOVA, what we're doing with the explaining the model portion, by random chance, that would be expected to be what? Which helps explain the F ratio and why the F ratio, if the top part is bigger, which is what we want. We want the model to be associated with the variation, not the residuals, which is when we don't have sums of squared error reduction in regression. So by random chance, what would we expect right here? We kind of jump topics. And great job right there. We're going to throw some 20 points to the chat while people think this over. The most likely, and exactly, if it's random, we assume that there's no relationship. And that's what you see over here. And that's why the random permutations have reductions close to 0, because a flat line is actually the naive model. And we'll be talking about these things shortly. I've hit upon so many topics, which we'll spend a good 10, 15 minutes covering, like what is the naive model, which in a quantitative model is the mean of y, which is where we get the sums of squared error from the naive model from. And then we look at the reduction from the naive model to our model, comparing if the line does a better job explaining than the naive model. And if the naive model is a flat line and our model is a flat line, the reduction would be 0 because our model is identical to the naive model. Let's hop back to space and see if there's more questions. We got free time right now. Ask questions. Whatever you're thinking. Maybe it goes beyond this class. I don't know. Stump me. Training and holdout. Andrew right here. Andrew appears. Let's throw some 50 points for a wild Andrew in the chat. Andrew, flex on the people with those points right there. I think you still got your crazy points. Let me make sure Andrew still got his points, because I reset the points every once in a while. Oh, of course Andrew's got his points. Andrew's got crazy points. His hours are real. I mean, his points, maybe they're real. Over 9,000 right there. Try to keep up with Andrew right there. William, amazing job right there, William. You're on track. Andrew took the class in the first group of students, and he was here well before muters don't even represent the true time Andrew has put into. And thank you, Andrew, for always swinging by and saying, hey, I miss seeing everyone around Knoxville. I miss seeing that sun sphere. I'll be back, though. I'm working out, Andrew. Getting in better shape, taking some walks, doing some push-ups, trying to be strong. Just want to get back. I'm not old man Brian, because I'm going to get back to Knoxville and be in my 40s. Which is, barely. We are back. Mohammed, so good to see you. Can't wait for the second session. Oh, awesome, Mohammed. Are you taking time series? Dude, okay, I don't... Yeah, no, it froze for me too. There was literally a stream issue right now. Andrew, are you taking time series also? I've got this amazing idea, which I'm totally going to ruin. It's based on South Park, and it's based on Marvel Comics. In the fall, well, if you're taking it with me, we might still be doing that. Can we estimate R squared and beta coefficients as well? Oh, are you doing beta weights? Can we estimate R squared? I guess I'm trying to think if we would, I can show you to find R squared, because R squared is going to be the percent, like you can do the sums of squared error to do R squared, because sums of squared error 1 minus the remaining variation out of the total will be, make sure I'm doing it right, because R squared is the percent of variation we explain, so whatever's left over, it's the complement of what we've left over. Does that make sense right there? So R squared is going to be what we explain versus the sums of squared error is what we have not explained. So looking at the total, the mathematics for it would be the total is going to be the denominator on here on the bottom. I can write it out in a moment here. We have what total variation there is, and then total minus unexplained is explained. So our goal is to reduce all the sums of squared error. So a lot of times we talk about things like understanding what is the error, what is the R squared, because the R squared is going to be percent of variation explained. R squared is super important. Like, oh man, R squared all the time, percent of variation explained and Y by the X variables in the model. Awesome work right there. And so I'll mention my idea right here, and then we could go into some R squared if you want. Definitely, like, and you're talking about beta coefficients. Are you talking about beta weights? That's something a lot of times used in social sciences, I believe. No, you're talking just betas for the coefficients in the model. I know what you're talking about. Of course, because, yeah, beta's the truth. Yeah, let's actually talk about that. I plan to. Let's talk a little bit about regression in those betas. I just needed that last sip of coffee. Let's hop over here to the main screen. Oh, and then we got a Simon question. I'm going to answer the quick question right here on betas for a moment, and we'll just mention what this is, because this will be coming up Monday next week, and it is on this test, so great question right there. Let's talk about this. Okay, 2 seconds. Let me get Word open. How did Brian not thinking beta weight social sciences? No, we don't do that here. We do betas, though. Let's go talk about that. Okay. So, and then we'll answer Tracy's question. Let's do this. They are talking about the following. They're talking about the mean of Y given some X is equal to the true intercept plus the true slope times the X1 variable. Very important right here. Now, we don't oftentimes use this because the truth is an unknown quantity. Unless we have the population, we'd never really know the truth. So our model creates estimates of these coefficients. And what we use most commonly in our class is going to be the predicted or estimated Y is equal to the estimate of the intercept plus the estimate of the slope times the X1 variable. So if you look right here in green, we have the true model, which is if we had all the data and what we truthfully want to understand, where on the bottom we have the estimate. Now, there's really great ways, just to mention briefly how to do this in R. If we have a model right here, we can actually come up with estimates, and this actually goes back to the normal curve with the 60, 68, 95, 99.7 rule. If you notice right here, our standard error, which is our uncertainty in the estimate of the slope right here, which is the slope of the line you see in the background right here, which is a slope of about 5, the rise over run of the line mathematically. You'll notice that the uncertainty is about a quarter of that at like 0.25. Now, when we create a 95% confidence interval, we'll actually use a t-statistic. But with enough degrees of freedom, you're basically using a z, and the z is basically 2. More on this in class and more specifics. But I can tell you that my interval for this is going to be about 4.4 to 5 point, I can't even think right now. To that, right? No. Let me re-clear that. Oh, no, now I need to see that summary. 4.43 to 5.43. Good. Let's go ahead and run Confint. Confint creates confidence rolls. What are you doing, Confint? You don't want to create things today? If you don't want to create things, we'll do it up here for you. Confint creates confidence rolls to the model, and I want you to look at this. How far off was my estimate right here? Not that far off. And I'm doing an estimate in my head right here by saying I'm about 95% confident that the slope for the line is contained, or the true slope, because this is the estimate. This right here is B1. This is B1 because it's the estimate of the slope. And then down here on the bottom, we have our estimate of beta 1, which is what they were talking about right there. So this is the estimate for what beta 1 might be, which is a truth that we don't know. Now, there's going to be something super important right here, which goes back to the previous thing we talked about. What do you notice is not contained in this interval, which is super important for statistical significance of a slope. For the slope to be statistically significant, we would not want what? We'll do Trace and Williams' question next. And this is on our test, actually. For the slope to be statistically significant, we wouldn't want that the true slope might be what? And it's actually in the picture over there. So we test it's beta 1 different to 0 with the t-test. Yep, exactly. And you see the t-test right here. And you can also do it with a confidence interval, and you can tell that it's not equal to 0, that it's different from 0. So you're actually seeing it two ways right here. Great answer right there. Exactly correct. We have the test right here on the coefficient of the slope, and this tells us that we have good evidence to believe that the slope is not equal to 0. And then down here with the confidence interval, same thing going on. The confidence interval gives an estimate of values that the slope might be in, and we are pretty confident that the slope is between 95% confident that the true slope of this model, which is what you were talking about estimating right here, the beta 1 is contained in the interval 4.44 to 5.41. And the reason I was able to make these estimates is it's basically 2 when you do a 95% confidence rule according to the empirical rule. Let's take Trace's question. Thank you so much for that question. Keep asking. I don't know why I thought about beta weights. I just got to take that out of my head. Something social sciences do that we don't do. They standardize their coefficients and models with beta weights. I was ready for a question that I don't usually handle. I was like, oh yeah, this is B1, B0, beta by 1, 0, 0. I got to stop overlapping what we call things, because we do that and then it gets confusing. We got 2 words for something. Trace's question was, for assignment 3, could you explain number 1 and why? Yeah, let's take this right here. I'm going to take this question. Let's go back, do some assignment. Thank you so much, everyone, for being here and asking these questions. Okay. I'm adding in the question. I'm going to show you a cool trick. You ready? Let's head over here. If you notice, I have a whole bunch of lines of code. I'm going to hit Control-Shift-C. Wait, what? That's what it does there? Cool. That's awesome. That's cool. Sounds like a fun class. Looks like it just commented that out. What does that look like? We're going to look at over here in the Markdown editor, just to see what it looks like, because I did the comment. Sure. Oh, yeah, because I'm in the Word portion. Well, no need to comment it out then. For assignment 3, could you explain number 1 why X equals mobile device and Y equals click on ad? Is it because the type of mobile device can determine if it is a touch screen to click on ad? I think oh, I see what you're saying. So let me rephrase this. Click on ad. Yes, no. Did someone click on the ad? Mobile device. Is someone using Samsung, LG, iPhone, of course? What mobile device is someone using? And then does that mobile device explain whether or not someone would click on the ad? Because you might think like maybe we'll do marketing to people who have iPhones. Like, oh, if people have an iPhone, we should really market to them. Especially if the product is somehow connected to like Apple, then you're gonna want to market to people with iPhone. So does the mobile advice explain the variation and why people click on the ad? Not like did they click on it like. Because if you go old school now, you might think some, older phones are going to have like not the ability to click on the ad. So then it would still be like the mobile device would explain if people are clicking on the ad or whether they're like going down on the D-pad, directional pad to click on it. But does that make more sense right there, Trace? The click on ad would be like a yes, no, whether or not someone clicked on the ad. And then this would be devices right here, like, does somebody's device that they're using explain whether or not they clicked on the ad? So that would be that one right there. So hopefully that makes sense. And then I think William had on 5B. Let's talk about awesome trays. Keep throwing those questions. Keep throwing those questions. I really appreciate it. Let's hop back here. Turn on our chill music. Drink some coffee. This helps me put breaks in the video later whenever I just take a half-second break right here. What's the plan? Oh, yeah. Are you taking both, is it? So I can't promise that, there's going to be, if you're taking both, there's going to be a lot of exams, a lot of material. 475 is going to be very project-based. I'm starting a company, not literally. There's going to be a company called Quantum Analytics, and the whole theme of the company is you from the future are sending... don't tell everyone my whole idea. I want it to be kind of a surprise to some people, because I'm going to send out an email like the week before the class and be like, hey, tell me some fun thing about yourself, blah, 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 blah. And then I'm going to send people, I'm going to reserve the domain address at UTK, and it's going to be called like Quantum Analytics. And then I'm going to email each student and be like, hey, it's me, you emailing from this address from the future. I still like going to hikes. I still, am doing this. I still have a dog named this or whatever. I just want you to know that I'm working on this project for my company, Quantum Analytics, and I need you to help me out with this. And then I'm going to make a promotional video like, here at Quantum Analytics. Like, I probably need the voice for that or something like,
here at Quantum Analytics.
I'll work on the voice. But I'll make a promotional video, and it's going to be based on like Marvel stuff. There's also a South Park episode where they do this whole thing where Cartman's like, the parents hire these actors who are like, it's me, you from the future, and I'm here to tell you about how doing this will be bad for your life. But in this theme, the whole theme of Quantum Analytics is it's a company that you get hired at to send work back to yourself in the past. I signed up for the Quantum Analytics webinar, but totally forgot about it. So that's going to be you're going to get this email from yourself, from you from the future, asking you to do work so that they don't have to do work. Does that make sense? I don't know. I found it kind of funny. But that's the whole theme. And then I'm going to intersplice things that you tell me. What's your advice for people taking the two courses together? So 475 time series is going to be more project-based. The good news is that practicing coding in R will help you with both courses. So you just need to immerse yourself. The start of 474, data mining, starts out with coding in R. 475 is going to start with coding in R. My hope is that you're just going to propel yourself even further. Taking two courses in the summer is a good bit of work, and they're two upper level courses. Just reserve enough time. I'd be trying to code maybe 2 hours a day at least. I know that seems like a lot, but it's two courses. And just once again, email me whenever you're stuck. Muhammad, I'll reply. I already see I got one Discord message. Message me on Discord. Just get a hold of me and be like, hey, Brian, I'm stuck on this. This won't work. My code's broken. And we'll be using DataCamp and stuff like that too. It won't be required DataCamp, but also start some DataCamp now. Get your skills back running, and you'll be good. Let's hop over here, look at the question I'm taking. Oh my gosh. Email me, hop on the Discords. I really want to make the Discord open for like all... We might do some reorganizing of the Discord, maybe have like an R code section for people to talk about R code and stuff, and BAS 320, 474. But my hope is my whole department could use our Discord, which is not for me to ask my department to use our Discord if they want. Oh, thank you so much, Mohammed. I appreciate that so much. Let's hop over here and look at William's question. Let's do this. Thank you so much, Mohammed and Andrew and everyone for being here. The question was... Question B. Let's go take a look at question B. Yeah, I just like having some music on in the background. Nice and relaxing. At a low level right there. Change the permutation to 5,000. Is there statistically significant? Would you say this is practical significance? Now, I'm not going to quite do your question right here, but whenever we talk about practical significance, we need to quote a numeric number. So practical significance is the do you care? And I really can't tell you if you care. Let's look at this. We're looking at smokers and whether or not people tip who are smokers. Is it tips? It has a harder time running that up there when I put it in that mode. I'm going to switch out of this mode because it really doesn't like me in that mode. This is once again not your question, and there's not a variable tips. There is a variable called tip in USD. Tip underscore in USD. Be careful. Everything needs to be uppercased or lowercased. Tip the bill. Tip like the full bill? I don't even got the money for that. It's mad about the graphics right now. Is he gonna like, is there another thing it's mad about? Now it's doing it. Now it's doing it. 20%. I think 20% is good. Let's talk about tipping here in a second and my views on it. Really? Really? Okay, let's run this. Oh my God. Really? I'm just going to break everything. There we go. There we go. There we go. Well, first off, this one leads to a non-statistically significant result. And you'll notice right here, if we're comparing means or medians, all of these results are not statistically significant, so they can't be practically significant. So good kind of review there. Like, not statistically significant results here are probably due to random chance or likely due to random chance. Can't be practically significant. Do smokers spend more? We're just asking questions till we find something we can actually talk about. We first need the doorway of statistical significance to get us to examining possible practical significance. Nope. Do male, female spend more? Surely. Oh, we found something. We found something. So we found that. Let's look at the difference between males and females. Quote for me the quantitative amount for. We're comparing means right here. Can we adjust for gender after that? I could talk about that next, or I'll do a little segment on that. Are you talking about like holding constant and seeing if that is a kind of lurking variable? Is you're saying like making a multiple model? I think that's what you might be talking about. Like saying making a multiple model that accounts for the variation of gender, such that we could see like we could subset on gender, or we could we could look at a model. Yeah, I'll show how to make the multiple model next, because that gets into what we'll be doing right after their first test. So good questions right there. Yeah. We can make a model that controls for the variation in other variables so that we could see holding that variation constant, is there variation accounted for like by the other variable? That'd be a multiple model right there. The multiple world. Good questions. So what is numerically, what is the practical significance? Numerically, what is the practical significance? You know what? I want to see who tips more. Let's see here. Who tips more? And we'll do it by percent. I might have to go back to the previous example. Oh, there's not a statistically significant difference there. Oh, what's up, Ronald? Yeah, I know I got the haircut. It's all gone. I'm sorry. I'll play my joke video next. I got a joke video for this. Great job, William, right there, showing the mathematics. I put it in the chat also. William is finding the mathematical practical difference. And then you have to ask yourself, do you care? Maybe at this point, I would say, if I weight tables a lot, a difference of almost $3, $2. This is how I would talk to people. I'd say of a difference of almost $3. If I'm writing a report, I might say a difference of almost $3, and I'd put in parentheses $2.76. On average, males spend if a male is paying the bill, they're spending on average that much more on the bill. And probably, truthfully, we should probably be looking at medians on this. Just to do another review type question. Yeah, there's skew to this. So we in truth, we should be using medians. We talked about QQ plots for normality today, or normal quantile plots. And you do see a little bit of right skew, especially the high outliers. Don't look at the histograms. They're there to trick you. These are our lines. And then you see these points right here are not within our lines. So we're really seeing a high departure from normality, especially right about here, where there's too much data on the high right side of the distribution. Also up here in the box plots, you see it in the pull towards the high right side. We could account for party size. We can make a multiple model right here. We'll do that next. Really great questions, because we got open floor on questions next. I'm always open to going above and beyond. And Andrew's taken quite a few courses here. We can account for party size and gender right here to see if maybe those are like, maybe when the male is paying the bill, maybe there's a larger party size. Maybe can we transform to the log? Oh yeah, we can do all these to estimate the difference. Oh yeah, boom. We'll do that next. But so here's the biggest thing. We're going to do all these big questions next. These are really good, like so many things. I'll show you some really cool stuff. We got a really cool function in this package right here, which will allow us to analyze that. Let me think right here. It's a quantitative. Actually, we don't have a function for a certain thing. We have a function for another thing. I'll show you a few functions right here that we got. And I could maybe write a function to do a certain thing that you're asking about right there specifically. But does this make sense, William, that this amount that you just calculated, So William calculated the difference right here. And now the really hard question is, do I care about that? And that's not for me to say for you. The answer is not yes or no. I mean, the answer is yes or no, but then there's the follow-up. If you write yes, you just can't write yes. You have to write, like, this is why I care about this. This is why I don't care about this. Like, tell me what the difference is numerically, and then tell me why or why not you care about it. You might not. You might say it's $3. It's not going to make that big a difference. Or you might say, that's $3. That's going to be a lot over time. So it all depends. It all depends. And let's look at some big questions right here. We got some, I really like people trying to stretch our thinking right here. Let's do this. So there's a little more advanced questions, which you are going to get to in this class. I'll show you some really cool functions right here. This goes into the concepts of R squared, goes into the concepts of transformations. For question number 2 on assignment 3, could you go over calculating the marginal distribution? Yeah, let's do that really quick. We're going to do Trace's question since it directly relates to what we're doing right now. And then we're going to hop back into these other questions about R squared, multiple models, and transformations. That's such a great set of questions. R squared, multiple models, and transformations. And we do, once again, if you're like, oh my God, man, my brain. We do all these questions little bit by little bit. Like right here, we're going to look at some marginal distributions. Let's go look at Trace's question on marginal distributions. And then we'll hop back and do some really advanced stuff, some fun stuff. Let's hop over here. Let's do this. So this question wants the marginal distributions. Now, where are the marginal distributions? Where do we see the margins? Boom. Look at that right there. We got some marginal distribution. Over here, we have a marginal distribution of gender. And so when we look at a marginal distribution, give the marginal distribution of location. So as a percent, I would like to know, so mathematically trace, tell me the marginal distribution of people who sit in the back. So go ahead and tell me the percent for the marginal distribution of people who sit in the back. As a percent. Like, marginal means out of everybody, so it's one variable that we're looking at right here. So report the marginal distribution of location. So we need to do it for all of them, for each location. So just think, for everybody, which is what the marginal is, it just looks at one variable. Like, you can just ignore this all here. We're just looking at only what I have highlighted right there. So the marginal distribution, once again, the margin, just looks at one variable, and then we're just going to look at the percentages right there. So what would it be for the marginal distribution of people who sit in the back? Great job right there. Excellent work. Is that making sense? That we're just going to compare right here and say, for all individuals. So this is out of everybody. Exactly. Boom, right there. Trace, you got it. You know what you can actually do? Let's grab these numbers. Kind of show some tricks. I believe what you could do... Oh my God. What are we doing? Let's go right here and just call this marginal. And let's go right here. And we got some quantitative values. There's a vector. What was the 579? Marginal divided by 579, and that'll give us those. And I'm going to raise my screen up, and then we're going to go here times 100, and then, we can store this as x. I'll stop a step right there. Round x to 2 decimals. There we go. Boom. That's what we like to see. Trace. Does that make sense, Trace, right here? I've just taken the bottom row right here, which is for everybody, the percentage set in the back. What you could do, watch this. Let's go here to names. What are the names ordered on it? Back, front, middle varies. Back. Wait. Can I do this? Ooh, yeah, I can. Ah! Don't work more, just work smarter. That's what they tell me. And what's really cool is when you double click something and you highlight it, you can actually put the quotes around it. So by double clicking and then putting quotes, you can actually do this right here. And so we're actually going to take, and let's just store this as x again. We're just going to overwrite x. And then we're going to go to names of x, and we'll store in names. And then we'll go x. And there we go right there. There it is right there. We've made a nice, neat vector. The only thing we have printing to the screen at the end of it is the percentages. And if you just look at the steps, like, we're just kind of doing some more coding, so maybe we could display this in a report. Especially maybe we're grabbing tables from online, so maybe we just read in a table, and then weekly we print out, like, here's the distribution of people who sat in the back of the class, front of the class, the middle class, the varies of the class, and we can put it down to a certain decimal place. So just think about how your code kind of goes through these steps. of taking in the vector, turning it into a percentage. Then we rounded the percentage down here. So let's kind of order that. So we just overrode x with a rounded percentage. We created a names vector. So this is now what's called a named vector. So position 1 is position back of this vector. So you could literally go here and do position back, and it'll print that. Or that's the same as just going here to position 1, which is position back of the vector, by making it what's called a named vector. It's just the same thing as a vector. It's just like, this is position 1 called back. It just has a name to it. So tables themselves, if you ever make a table of a variable, a table is also a named vector. It's a type of named vector. So you could go here, store the table as x. Don't put all this code in your thing. And then you could go to position female, and it'll give you that right there, because a table is a named vector. I didn't know that for like the first year of coding in R. All the things I didn't know. That's a great question, Trace. Keep asking those questions. We're going to talk about those advanced concepts because we got open floor on questions. So let's hop over here. Let's play Celeste music while we do this. Not really Celeste. It just sounds like it to me. Let's hop back to the main screen and let's take a sip of coffee. Let's do those advanced questions. Keep asking questions if you have them, though. Let me know. Throw those questions out. Let's do this. Okay, so the questions we had were kind of like multiple models, R squared, and transformations, which are definitely things. We even mentioned transformations a little bit today. Two big reasons we use transformations. Well, one, most often, is to create normality in the data. So if you see something that's highly skewed, like Survey 10 has some highly skewed variables, like how many texts do people, how often are people on Facebook? You can already see a little bit of this skew right there, but if you take a look at this, I'll disappear here. You can see the right skew nature to the data. So one way to fix things like this is to throw a log 10 around it. We don't want to do it around the histogram. We can make it easier to understand what we're doing by going here and taking the original variable and storing it in x. That's just what I store into all the time, and doing a log 10 of it. Really? Really? Oh, because I'm not doing x. Haha. A bit better. Got some left skew to it. We have a function. I'm trying to remember if I remember it. I could rewrite it, but I know we use it in 474. I just can't think of it. What we actually have in 320 right now is if we look at two variables. Let's go to find transformations. So this basically does the same thing. When we get to regression right here, which we'll talk about multiple models in a moment, the linear model function, which I often store into M for model, creates a linear model between two variables. And what do I mean by a linear model? We're just talking about it looks at the linear relationship by fitting a line between two variables. And we can see this right here. But if you notice, the model might not have some linearity at the top side. It could have some outliers. And this is, let's try with gender and cost. Oh, for the last data set? Yeah, let's do that next year. You got it. Here's a really cool function right here. This is the find transformation function in the reg class dataset, which we will see in 320. And what it's going to do is it's going to try a series of transformations. You can actually see if you look at the help function right here, the find transformations is going to go from a power sequence of -3 to 3. When it hits 0, it'll do the log of it, and it's going to see if there's an increase in R squared. So it actually goes through here and looks at the R squared with all the different transformations. Does this make sense here, what's going on with the find transformations? It's saying that the original model had an R squared of 0.361, which is the percent of variation in Y, which is height, explained by the variation in weight. And then when we do the transformations, we see here that we obtain an R squared of 0.41, which is a higher R squared. We can also see the plot of, oh, that's the no transformation. Here's the higher transformation. Still an outlier, is massively impacting our abilities. There's probably that one over there. But this is now the transformed model right here. And we went through a series of sequences. Yeah, it's really good for looking for transformations. It goes through and it also does log 10. So when it hits 0, when it goes from -3 to 3 across the transformation powers, so it literally permutates all the transformations and then creates a list of all the transformations. So in this instance, I might not do a transformation right here. We might look for a non-linear relationship in the model. And we've actually got a function for that with choose order. And choose order is going to help us examine, there's the R squared adjusted, which is accounting for multiple models. It looks to me more like a polynomial model would be a better fit, which is fitting a nonlinear relationship to this. So I don't think transforming the variables might be our best option in this instance. We get a little more out of a fourth degree polynomial, which is going to be this blue line right here. So just different techniques right here, whether we choose a polynomial model or we go with a transformation on the variables. Either way, this data is a little bit messy. But you can see here, when you reach the fourth and fifth degree polynomial, there's a sudden shift in the ability for the model to go through the data and reduce the R squared. Reduce the sums of squared error, which goes for an increase in the R squared. Here's the linear model. The second and third degree polynomial have a good increase to the R squared adjusted, which accounts for the multiple model world. And then the fourth, fifth, sixth degree polynomial also see a sudden shift. And the fourth, fifth, sixth degree are very similar. And if you know Akaike's information criteria, it's definitely pointing us in the direction of the fourth degree polynomial, as is the R squared adjusted is pretty close on it. I'd probably go with the fourth degree polynomial, which is going to be this blue line right here. These are things which we will cover for a good 20, 30 minutes in class. Do not worry. We'll do lots of examples right here. But this is dealing with a polynomial model, which is going to be a multiple regression because we are now using our x to create an x squared, an x to the third power, and x to the fourth power, which allows the model to have bends through it. So instead of changing what x and y are through a transformation of the model, like changing literally the values of x and y, because you notice right here, height goes from 55 to 75. Oh, what's up, Devin? It's still around. There's the flow. There's the flow right there. What up, Devin? Some 20 points for Devin showing up right here. Good to see you, man. So you can see the difference between the approaches of transforming the variable versus fitting a polynomial model. And then this brings us back to another question about, well, cool, this is the multiple world with a x brought to the x squared, cubed, quadratic, quintessent, oct. I don't know. Y'all know what to call those things. Let's look at a multiple model, though, where we're looking at the tips data set. I'm always happy to see you stop by, man. That's always good. I love seeing students drop by. We have Andrew here today. Andrew swung by. I think we had someone else swing by. I'm trying to think who else swung by. Andrew swung by. You swung by, and there was Muhammad came by. Muhammad, Andrew, Devin came by. So good to see you all here. And so we were asking if gender plays a role. And here's how you do a multiple model in R. The interpretation of after this polynomial looks different to men. Thank you, Devin. Explain in greater detail. I'm trying to make sense. Like, we could. Thank you so much, Evan. You're so awesome. I'm throwing another 20 points out there, Devin, for some positivity right here. So we could control for. We could see if gender's still going to play a role, I think. So actually, let's take the data set we have right here, the multiple model, and we could see if gender's playing a role right here. I wish we had a code. So you're saying, let me read it again. The interpretation after this polynomial looks maybe like gender probably still plays a role in this. Like, I would think that, and what we're actually going to do there is you'd actually be creating indicator regression with polynomial models. We don't have a good visualization for that, unfortunately. What you would see, I can show it right here. If you were to do this as a indicator regression with polynomial models, I just don't think we will visualize it. What you would get is you would get one polynomial model like that for men and one polynomial like this for women. So you'd see the indicator coefficient is going to be denoted by this difference right here, which will be a constant difference for men being the top line and women being the lower line. And that's going to be an indicator regression where a categorical variable is used, which I'm just going to throw the pen. And once again, what I'm drawing here, let me draw it in a more simple format. We've got right here our data, which a polynomial bend through the data. And then we create right here a line for men, which is a polynomial bend, and we create right here the polynomial bend for women, and this constant difference right here is the coefficient of the indicator. Does that make sense right there? This is a multiple regression polynomial with height. We could say we're explaining the height of individuals by the weight, and we're including in here a male and female. Sure, that's crayon. And unfortunately, I don't think we have a good visualization for this. Like, we can do indicator regression without the polynomial model, but I don't think we currently. It'd be cool if it visualized it, but I don't think it will. But that is a multiple regression polynomial model with an indicator variable. Yeah, awesome. Yeah, the visual always helps me to see it. Usually we think of like an indicator variable. It's a constant change in the coefficient. So it's a difference between the intercepts. And we'll also be covering this. We have a whole chapter over this. This whole thing right here that I'm talking about in 1 minute is a whole day and a half. It's a good 2-hour talk. Could we do question 2, problem D? You bet. Let's do it. Let's do it. Hopping back over here. I think I have the code, but a bit confused on the analysis part. Thank you so much. Great questions. Making me think right there. It's always good to like think about how we visualize stuff, and it's tough. It's the problem with inquiry, because if you don't know what you're looking for, can you find it? If you know what you're looking for, haven't you already found it? The DPD right there. Conditional equals total equals conditional divided by total. That might be it. I think you've done it. Trace, I think you got it. Let me go take a look at this. Does it want the conditional display of like males or females? I think you got it. Yeah, let's take a look at that. I'm getting it all set up, but Trace, great job. That looks correct. I don't see really a problem with it. Might be wrong. I don't know. We'll double check to make sure it's the code for females. Okay, let's take a look right here. And let's go over here. Let's hop in and let's take a look at this. Let's do it. So we've got the conditional display right here. The conditional display is going to be just the vector for one of the groups. Let's confirm that that is the right answer. So we got right here the vector for females, which we can just copy paste and put in there. So we've got the vector for females, and that is right here, 62, 127, 126, and 14. Excellent work. And we don't need the last total because that's total amount. That's a marginal display. Hence, in the margin. Margin. And that's the grand total down there. So the way to think about a conditional display, which I know it's highlighting that number, so we just won't use it. The way to think about a conditional display is given somebody is female. And so let's double check. I think there's an issue. I think I see it. I think this is incorrect. And I'll tell you one way I know instantaneously. Don't worry. The reason I know is that a conditional display will add up to what? So you actually do have conditional displays right here. You actually have done conditional displays differently. You've done conditional sitting in the back, conditional sitting in the each one. What should a conditional display add up to? What should a conditional display add up to? The conditional display, like, how do you unzip a file in R? I've never tried unzipping a file in R. That's a good question. I would unzip it outside of R. I'd right click and then uncompress and choose the file. It should add up to 100% correct. So if you notice, I just deleted your vector right here. What is the total you think we should use when we're talking about given someone is female, what's the probability they sit in the back? Given someone is female, what's the probability they sit in the front? Given someone is female, what's the problem they sit in the middle? Given someone is female, what's the probability they sit in a varying position? So like where they sit in the class. So the location, what do you think we should divide by to find out the percent of females who sit in the back, the percent of females who sit in the front? So, yep. Bingo. And now look at our vector. Nice. There we go right there. And once again, we can take, we could go here round on X. Doesn't hurt to do that right there. And there we go. Exactly. You know what's really cool also? We've already got that names vector. Great job right there, everybody. We've already got this names vector right here where we gave the names of this. Where we calling this, you know, just call it lowercase x. Not s, x. There we go. We call it, we go right here and go do this. It likes that, right? I don't like my code to go off the screen a lot of times. You can always, after a, there you go. Looking good. So there would not be significant association. Let's go ahead. I think we still got the x vector, right? Wrong x vector. Let me run this. Okay, I think that's got it. Did I just overwrite x? No, it's lowercase x. Okay, cool. Yeah, I mean, look at this right here. And you know what? Let's make this smaller. I just don't like how long the names look because they don't really match up well when I do that. There we go. And let me overwrite x with this. So that way I can... There we go. Okay, here we go. So this is the way to look at it right here. We'll make it nice and big so everyone can see. And your answer for if there's evidence of an association. So when we talk about an association, it's when you know like somebody's gender, would that give you information about where they sit in the class? So generally speaking, you know, 18% of people sit in the back of the class. 18.48. I was going to say 18.5, but I'll be exact. 18.48% of people sit in the back of class, where if somebody is female, given that they're female, conditional distribution, 18.84% of them sit in the back of class, which is basically identical. The probability of somebody sitting in the front of class, given they're female, because this is conditional, given someone is female, what's the probability to sit in the front is 38.6. And just generally speaking, it's 37.31. So that's pretty similar also. This one over here, the varying position, 4.26 for females and 4.15 for generally all individuals, because this is the marginal distribution given just like all people. What's probably someone sits in a varying position, then yeah. Does this make sense here, Trace? I didn't directly say the answer, but I think you're kind of seeing it. And this is also, one thing I love is this, what we're talking about right here, is maybe this right here. So if you look at the visualization of this, you can kind of see what's going on right here. So you can see if much of anything is going on right there between the two. I mean, there's small differences, but those differences are probably due to random chance. Great work. Great work. Everybody, amazing work. Great practice. Did you say you're doing medical stuff and like learning R for that and practicing up? If so, great job. We're honored to have you here, and keep asking those questions. I'll keep trying to intersplice them, especially when we have a downtime and don't have questions. Can we use chi-squared to estimate if there's an association? Mm-hmm. And that's actually what we're doing right here. Good question. That's 100% related to what we're doing. We were doing that earlier today. Where is it? You can actually click through the notes right here. So here we go with the chi-squared, and we see another question right there. Yes, I do not think there's an association, but wanted to make sure I was thinking the mosaic plot, how we talked about the exactly. And we see that right here where this is evidence of a strong association. This is evidence of a weak association, which would have a high p-value, or not evidence of a weak association. Lack of evidence for a strong association. So this would be likely by random chance. This would be unlikely by random chance, a stronger association. Sample size does matter, but we'll just assume we have adequate sample sizes. When you see something like this where there is differences, i.e. discrepancies, then those would be unlikely by, could or could not be unlikely. It just depends. So this is exactly what we're doing right here is we're running the chi-squared test. Well, thank you so much. It's years of practice, and Dr. Petrie is my mentor, and I truly mean that. He's taught me a lot. So just keep asking those questions. Just keep working away. I have to push myself because I teach, so I'm always trying to learn and get better. So when you're asking about the chi-squared, here is the chi-squared right here. The observed minus expected squared over expected is going to give us the discrepancy. And this value right here, although we're calling it a discrepancy, in classical statistical sense, is the chi-squared test statistic. More specifically, this is a cell chi-squared, because to get the chi-squared test statistic, we have to add up all the cell chi-squareds. So we were talking about this today, especially that we have the row total times column total over grand total to give us the expected counts. And once we get all the expecteds, we can go down here to the formula and do observed minus expected squared over expected, which are cell chi-squareds. But most importantly, we sum them all up to get the chi-squared test statistic, which we're just calling a discrepancy down here. It is a chi-squared test statistic, but it's also a discrepancy. And what are discrepancies? Discrepancies are really just the differences we see between the marginal distributions, or comparing a marginal to a conditional, like we were just doing in the assignment right there. So that blue line right here, I'll circle it, is the discrepancy, where we see small discrepancies over here, which are likely by random chance. So the discrepancy here might be something like 2.4, where the discrepancy over here might be something closer to 40 because we see larger discrepancies. And once again, this is in classical statistical sense, the chi-squared. What's really interesting, because you might say, well, why are you not just using the chi-squared? The reason we're not is because we're not actually using it. We're actually simulating results. And I shouldn't have so many things open. Here we go. We are simulating results and actually creating. Did I have a lot of high seed? No, I didn't. You can load. Figure's too large. Wait, what? Oh, wait. What is going on? I want to reappear. Where's my see? Compliment my R skills and something breaks. Let's clear out the plots and see if that fixes the issue. You can plot for me? There we go. There, it did it. This is actually a simulated chi-squared down here, so we're not actually using the chi-squared, but it's actually not coincidence that we get a chi-squared, what looks like chi-squared with 2 degrees of freedom. Reason 2 degrees of freedom is this is a 2 by 3, 2 by 3, reduced by 1, 1 times 2, 2 degrees of freedom. So the distribution you see down here, and we'll have Mubot bring up the chi-squared.
I am Mubot.
Thank you, Mubot. Send out that chi-squared link in the chat. The chi-squared distribution, which you see right here being simulated, is going to look a lot like this, which you see it goes about to 13. And you look at where ours goes to. Wow, not a coincidence that what we are simulating via permutations, which we use permutations to simulate results right here, which is non-distributional based then, but it, funny enough, mimics the distribution, creates the chi-squared. If you don't do a lot of permutations, you won't be able to see it. But we could do 10,000 permutations and let it run, and it's going to simulate what would happen by random chance. And what happens by random chance, look at that, is almost, oh my God, I lost the right page. I thought I had it open in the background, is almost just like that chi-squared. I know it's super great. It's a very modern approach to doing things. If you look at where it really trails off, it trails off at around 13 or so. And if you look at where this trails off, it trails off around 13. Not coincidence that what we are simulating right here looks like the chi-squared. So we're not exactly using the chi-squared. We are finding our discrepancy, which is the observed minus expected squared over expected. All of those things are being calculated up here for us. And then we are looking at what would happen by random chance variation via random permutations. Once again, that's when you take your papers, throw them up in the air and just say, hey, whatever lands nearest to you is what you get. And then you can see our result right here in this red line, which is our discrepancy, is very likely by random chance, i.e. the results that would occur as extreme or more extreme than ours are results by random chance would occur 72% of the time. And this is not statistically significant, and we are confident about that because 0.05 is not in the interval. And I did way more permutations than we need for such a non-interesting questions. Is someone's handedness associated with their gender? Which if you're going in classical sense, the null hypothesis would be that there is no association between, quickest way to say it is, that there's no association between gender and handedness. So yeah, no association. Just when you look at two variables, not associated. And that's the classical kind of null hypothesis sense. Well, let's see. Any last questions as I just try to break my microphone here? I tried. Didn't achieve the goal. Really great stuff, and it really comes down to practice. Go back in time and talk to 2015 Brian, who was just starting his adventure in coding in R. And I would not have the skills I do today. It's about practicing. It's like playing an instrument or training your muscles. For 2E, does it matter that there is no association to calculate the expected count? Nope. Doesn't matter. Great question. And so to calculate the expected, row total times column total over grand total. You got that right there, Trace? Does that make sense, Trace? It doesn't matter that there's no association. You can always calculate the expected. And the expected is just the classical multiplication rule because it's row total times column total. You're just seeing like what you would get if you multiply these together because you're not taking into account what actually exists. It's just rather interesting to me. Let me talk about that briefly right here. And talk about why it's just the multiplication rule. The multiplication rule in statistics has with it the rule of independence, which is what we assume, especially classical chi-squared test of independence. So let's go take a quick look at that. So when we do an expected count, it's looking great right there. The formula is actually a little more complicated than that. That's exactly the way to do it, though. Here, I'll do it for, because you're doing 329. Are these the numbers? Is it different numbers? Oh, I've got different numbers right here. Good. I've got different numbers. Yeah, so permutations are... Yeah, oh, and if you go to Bayesian, Bayesian stuff is good right there. I need to get better at my Bayesian game. If you want to stump me or ask me some things where I'll tell you I have to look that up, start talking about some Bayesian stuff. Start talking about some given, some some prior and some posterior. I mean, I'm not a Bayesian. I'm more of a like a computer scientist type statistician who uses brute force with like Monte Carlo simulations. Everyone's got their own form of stats, and every one of our statistics is the best. No, Bayesian's really great and really interesting. A person in our department, Humphreys Bosdogan, huge on Bayesian, and actually knew Dr. Akaike, who made Akaike. Well, not just knew, he was his mentor. Like, not like I say, Dr. Petru's my mentor. He's like my encouraging person who helps me out. But Dr. Akaike, Dr. Humphreys Bosdogan, went to Japan for like 2 years postdoctoral work and studied under Dr. Akaike. They met at a conference, and Dr. Akaike was impressed with Dr. Humphreys Bosdogan's work. And really, really cool story. And yeah, if you know who Dr. Akaike is, he one of Japan's top scientists. Really great guy right there. And so here's how you get it. Row total times column total over grand total. So that would be for ambidextrous female. That is correct. And what's interesting is we're actually doing the formula. This is the probability of somebody being female. This is the probability of somebody being ambidextrous. And the formula looks a little different right here. And then this right here is going to make it so that it's not a percent anymore. So if you look right here, the mathematics for this is actually the multiplication rule in 201. Like, what's the probability of someone being ambidextrous and female, or female and ambidextrous? Does that make sense, Trace? Like, it's the multiplication rule in 201 because you assume independence to say what's the probability someone is female and ambidextrous, and then multiplying by this right here will get you not the percent anymore because this is probability. Multiplying by the grand total will get you a male and ambidextrous. There you go. Oh, thank you. I appreciate that so much. That's my goal. I appreciate that. That is my goal. Look at that reduction right there. Now that we've reduced it, what is the formula? So this is the long way of doing it. I almost did this in class, and I was like, it's going to take another 2-3 minutes. And I know 2-3 minutes just add up if you go into explaining everything, like the minutia of it. But that's what we're doing right there. But when you reduce it, you're really just doing the row total, which you can see right there is this is here. I'll mark it in different colors so we can see it. This is the row total. This is the column total, and this is the grand total. So this is the row total, column total, grand total, and you're literally just getting the formula row total times column total over grand total. So when you reduce it, and that's the expected count. So it's using the rule, yep, row times column over grand total, exactly, boom. So you're doing it this way by using the rule of independence, by saying what's the probability of someone being female and ambidextrous, assuming independence, because that's what we assume to start, is that two things are independent when you multiply them together to see what's the probability of these two things happening by random chance together. Rule of independence, multiplying in 201. And then down here on the bottom, we've just reduced it because 699 and 699 cancel because you have two grand totals right there. So once again, these are grand totals and they just cancel out with each other because they're both one numerator, one denominator. So mathematically they cancel, and you're left with the following formula right here: row total times column total over grand total. So great stuff right there. Keep asking those questions. Try to stump me. I don't care. I'll tell you I don't know. If we start talking Bayesian, I'll just keep saying prior and posterior. I'll be like, yes, Bayesian, prior and posterior. Great stuff. What's the probability of A given B? Now we're talking Bayesian. No, Bayesian's really good. I have problems with Bayesian for the historical method, though. A lot of historians like to use it, and I'm like, if you pick your prior, and you can just find any posterior you want. So the picking of the prior in Bayesian is one of the most important things, and that's where controversy can hit. If you go and start going to subjective priors, then your posteriors, you throw subjectivity into your prior, you're going to get subjectivity into your posterior. If I download a data set from the web, how do I put it into RStudio? It's a CSV. We got a function for that. What function should we use? Let's hop back here to Spice. So there's two ways, especially to read data into R. I'm just going to make a little cut right here in the video, because if you ever come back to these videos, you notice the cuts. So we can answer Andrew's question right here about how to read data into R. And there's kind of the answer. How do we read data? So if you're ever looking, let's hop back here. So if you're ever looking how to read data into R, I would start by typing read. I guess you could put the space or not the space. But with the read, you'll see all your options. I might have some extra ones. A really great package is going to be read XLS. You don't need it. And if you don't have read XL, it's read XL apparently. You want to install that. So the hair, oh, what's up? Hi, good to see you. I know I cut it. I'm sorry. So good to see you. Hi. Excellent work. Good seeing you. We're going to throw some 20 points random high appearing right here. I had long hair if you didn't know that. We have a visitor from across other side of the world. I wonder if it's like 8 p.m. where they're at. What time? You'll have to remind me once or twice how to pronounce your name. And what time is it where you're at? It might be like 1 a.m. Might be like late night stats. So what do you think? I'm going to put some options on the screen here. We're not going to use read Excel. What do you think you'll do? And it wants the file path to begin with. The read function reads in files. So the dot then goes to the file extension. So ftable is actually not a bad one either. I think it can take multiple file extensions. It's 11 p.m. Awesome. Good stuff. That's late night. That's awesome. Do you say, try to remember where you're from again. That's awesome. We're honored to have you here. It's just a lot of fun. It's still trying to loading. I'm trying to get data from CDC. Oh, cool. Doing some CDC data. Maybe send, maybe we'll hop on Discord after this. If you want to read in your Fortran data, here's how you read in your Fortran data. You notice here it tells you the package extension, what package these are coming from. So just take a look at that if you're wondering where your packages are. It's base R, which means it's like freebie stuff. Everyone will have base R. Utilities, I think, is also base R. It's just, no, I've never installed package utilities, so I think it comes with base R. It's not like base R, but you'll have it. Yeah, I don't see any other ones. Read Excel. Read Excel is pretty good. And then this is a way of going into a package without loading the package. So, and I rarely use that. Yep, we'll hop on Discord. Let's do that here in a moment. Like if I want to go to ggplot. Oh, maybe I don't have ggplot. Let me see here. Do I have ggplot? I reinstalled R lately. I don't have ggplot. ggplot is a way to graph stuff. ggplot 2. What do I call it ggplot 2? Where's ggplot 1? So now it's installing ggplot. Got ggplot, a bunch with scales. It downloaded a bunch of kind of packages I also need. I can go here to ggplot 2 and call functions with inside of it. This is kind of a lighter way of doing stuff. Like maybe you're worried about the time it would take, so you don't want to spin up a package. So if I want to call ggplotly or something like that, which actually, yeah, there's ggplot. So this is resourcing the package without loading the package. Because maybe you're like, man, it takes so long to load those packages. Probably a better way for people who do a lot of coding, especially if you're maybe sending people code and you're like, hey, run this code. You might focus on doing this. Like that might be the advantage. I just load up the package and then I get the autocompletes. I don't know. I'm probably not the most time efficient coder in the world, but who is? Not me. Well, that's got it. A lot of great questions about reading in data. Keep swinging by, asking those questions. We'll hop back here to Spoice. I think that's got it. Trace, Andrew. You'll have to remind me how to pronounce your name again. I'm sorry. And Devin. Awesome to see you, Devin. We had a bunch of people drop by. William, Muhammad. Great seeing you, Muhammad. Devin also. And hi, good seeing you. So many people. Awesome stuff. William might still be here. Great seeing you. Can we save our Excel file? Yeah, of course. Let's show that real quick. Yeah, definitely. Let's do it. So I wonder if we have the right. So here's how you read in files. You read in files with read, and then you write files with write. Can we write Excel? You can write a CSV. A CSV is a comma separated values or comma delimited, comma separated, which will open up an Excel perfectly fine. For some reason, the read Excel package doesn't. Is there a write Excel package? Watch this. My mind's gonna just be like, wow. Oh my gosh. There might be a write Excel package. Oh wait. I don't know what I just downloaded, but we're going to find out. Oh my gosh. Okay, I just loaded up Write Excel. No way. Look at that. We can write an Excel file now. You want the Write Excel? I just kind of guessed what it would be. I do not know what this package is exactly. It's on the CRAN server, it seems. Seems legit. Haven't looked at this package yet. You can always look over here at your packages to see what you got. I mean, it really only has the function XLW version. Yeah, I know. Write Excel. That's what it is. And so Excel hyperlink. Can I click on that and then look at? See, it's nice. They show you what the function is. Write Excel. So there's the Write Excel function right there. So you can take a look at the functions and see what's going on with them. But yeah, write underscore XLSX. And here, I'll try writing one and we'll take a look at what it gets us. So we could take a data frame we have right here. Like, let's take the survey 10 data frame. Let's go to write XLSX. That's going to write an XLS file format. You need to take the data frame, wherever you want to write to Excel. That's the first argument, as long as I know how to do this. The path is going to be, let's call it sur10.xlsx. It ran. That's a good sign. 2 seconds right here. Let's go find out if it's on the computer. Oh, it is. Oh, it is. No joke. Check it out. Look at what that says up there at the top. It says sur10. There, we did it. sur10. We've done it. There's where I was writing sur10 right there, and there's your sur10. That is written to Excel with XLSX format. It even put, which is kind of nice, my columns are not really spaced well, but they're bolded, which is kind of nice. Yeah, that's great. Hey, I'm throwing some 20 points right there, asking the big questions. It's questions, like I'm learning things right here. You know, I knew how the function kind of worked from write Excel functions. So if you wanted to write to an Excel, and if you double click, you can space stuff out. Maybe I could do this and then double click. Oh, look at that. Obviously. Better just do things all at once. Now our data set's looking a lot nicer. Did we do that? Gender. Okay, good. Yeah, I'll zoom in on this a little bit here. There we go. This is the same data set we were working with. Someone wants it in Excel format. Well, here you go. Here's the Excel format. Oh, the file is 43 megabytes and R only allows for 5 megabytes? What? Oh, no. I would think R... I'll watch this. Huge file. It won't accept that one that big. I tried to make a 74 gigabyte vector. That's a bad idea. This vector is now a gigabyte. It said no to that one. I used insert database button in R. Studio's dummy. Yeah, no, that works too. There's a bunch of the there's a bunch of those options up here. So I don't use the point click stuff. No, don't worry about that right there. The point clicks can work out really well, but I think the issue with the point clicks are they're not always updating them. I was like weird. Well, apparently there are limits, which I didn't know that. It just didn't want me to build a 75 gigabyte file. I mean, come on. If I want a 75 gigabyte file of random numbers, give me that 75 gigabyte file of random numbers. R said no. R, we're clearing your brain for that. We're deleting everything out of here. We're saying no to R. Say I can't make you your file. I say, well, I'm done with you, R. No more R for today. Bye bye, R. Well, this is too sad of an ending. It's too sad of an ending. We need something. Let's go to our 80s music. Let's put on a little hacker man. Let's go to pure 80s. Let's go full 100% 80s right here. Full 80s mode in effect. Stat 2-1 hacker man. Yeah, William's got some questions. Let's do it. We're hopping back into this. We're just going all 80s today. Could we look at question 3, C and D? Let's look at question 3, C and D. Let me get that going up right here. I'm just going to listen to the 80s music while we do this. Question 3, C and D. We need to go to page 71, exercise 3. Page 71, exercise. Ah. Below is sampling distribution. Okay, got it. So William, here, I'll give you some huge hints. You ready? Let's hop over to this. Puppet Shark, you ready for this? You ready, man? That's tiny Puppet Shark. Below is a sampling distribution where we have the F statistic calculated. All of these right here, William, are being calculated by what? So all of these results right here, because they're permutations, are just what's. And here's our result. They're permutations by random chance, exactly. So if we go take our result, I'm kind of alluding to the answer right here. What do you think about this, William? Ah, that's where the observed line is. That's where the red line is. I should have done it in red, right? Because that's what our notes show. Let me change this. Not that I've heard that song before. So that's what our notes show. What do you think about that? I think, you're like, I got it. William is like, yeah. So, I mean, that's what I like seeing. Yeah, I think the harder part is this doesn't show you the line. You have to then take this information close to definitely smaller than 0.05. There might be some, it's hard to tell. It's small for certain. I mean, the computer will calculate it for us, so we won't ever really, we should be able to easily tell, though, that that's a tiny, if anything, p-value, which is literally the answer to the question, which answer, yeah, approximate. You could say approximately 0. I'd take that, approximately 0. I wouldn't say it is 0. I would say it's estimated to be about approximately 0. Like, so the management only cares about differences in 1,000. So if the management only cares about differences of 1,000, we need to take this right here. Can I zoom in on that? Perfect. Here is a difference of 1,000. I don't want to directly tell you the answer, but that's a difference of 1,000. That's a difference of 1,000. So about that big of a gap is a difference of 1,000. I might have went a little too large right there. What do you think right here? What do you think? What do you think right here? Just looking at this, this looks to be one of the biggest gaps right here. And this gap is that's probably one of the biggest gaps because they're all kind of within that. Like that might be the lowest and that might be the highest median. And there's their gap. And here's this. I might have went a little, yeah. Yeah, and if you look at this right here, I mean, just estimate what that would be. The biggest difference looks to be between Monday and Saturday. I'd start quoting some values. I don't want to directly give away the answer, but I think, William, you're on the right track right here. If you look at the scale on the left, you can see what a difference of 1,000 would about be, and then you can see what the difference here is. And looking at this visually, I think there's, does that make sense? Like here is 4,000 to 5,000. Here's the differences. We see that's some of the largest differences. So, yeah. Does that make sense, William? Like, I don't want to directly say what the answer is, but I mean, I think I'm kind of showing it here visually by being like, well, we care about this. I think you get it. I think you got it. Let's hop back here to space. Excellent work, everybody. Excellent work. We know what's going on. We'll end off here with some Celeste today. Let's end over here with our fun goodbye music. Mubot, you doing well, man? Mubot, where you at? Mubot! No!
I am Mubot.
He's back. I don't have evil Mubot here. Getting everything all fixed up right now. Speedrun video. Got so many buttons. I'm back now. Well, with that, let's go over to Mubot's world. Oh, you're evil, Mubot. Evil Mubot. Why are you being evil, Mubot? There you go. You're back to normal, Mubot. Well, Mubot, It was a great day here at Stat Tool, and you got anything to say to the crowd?
I am Mubot.
That's what I thought. That's what I usually think about you, man. But we'll be back tomorrow doing some teaching, doing some practice. Great job, everybody. Just chilling out. Puppet Shark exists in this world because he exists everywhere. We're all here. We're just here to have some fun, practice some stats. 201-320, let us know. Or if you're just visiting, you have questions, swing by anytime. Here on Stat 201. Bye for now. Bye.
I am Mubot.
What are you mad about, Mubot? We got to end the stream sometime. We'll be back.